Okay, so in this video, what we're going to talk about is the common time bound of big O v plus E. We most commonly see this with graph algorithms where we can represent problems in terms of a set of vertices and a set of relationships or dependent relationships with edges. And often the biggest challenge with graph problems is that we don't initially know how to model the problem. The problem statement is just a bunch of words. But what we need to do is we need to take that problem statement and model the problem in terms of nodes and relate those nodes somehow, perform a search, and derive an answer. That's the shape that many graph problems take. But what we're going to do is we're going to lay the groundwork for understanding how to manipulate and work with graphs and understand the time complexities surrounding them so that we can analyze these problems, we can solve these problems, and understand how to approach these. What we have here is an undirected graph. We have a set of vertices, which is each of these circles, and we have connections between them, which are edges. When we have an undirected graph, then we're going to have no direction in the edges. We can go both ways. We can go from A to G, G to A. And then we'll get deeper into directed and undirected graphs. There's a lot of graph terminology, but we just want to hit on the time complexities with this video. Before we understand the time complexities of graphs, we need to understand the different ways we can represent a graph. We can represent this graph either as something called an adjacency matrix or an adjacency list. And I don't know if there's other ways to represent a graph, but these are two of the base fundamental ways. So an adjacency matrix represents whether there is a connection between any two nodes, and it looks like a matrix. Let's build the adjacency matrix for this graph just to get our feet wet with this idea. What an adjacency matrix is it's a V by V grid where V represents the amount of vertices. It's a V by V grid that represents, do I have a connection between any two nodes? So let's just fill this out and we can demonstrate what this looks like. For A, what can A reach? A can reach B, J, and G. So what happens is A cannot reach A, we put a 0 there. If we had a connection that cycled back to A like this, then A could reach A. But A can't reach A because it doesn't cycle back to itself. So we put a 0 there. And then we see that A can reach B, J, and G. So we put 1s on the nodes that A can reach. So let's represent that. So I forgot to add the J, I just added the J, so let's fill it out. So what we just did was we represented all of the places that we can reach from A with a row in the adjacency matrix. So if we were doing depth first search, breadth first search, to find the adjacent nodes, we would just say, A, who can you reach? Whatever is a 1 here can be reached from A. And now let's represent B. What can we reach from B? We can reach A, D, and J. So let's add A, D, and J. So you see that we gave them 1s and then we give 0s for all of the other connections because they don't exist. And now we can fill the row out for C. What can C reach? C can only reach H, so we can fill that out. And then what can D reach? D can reach B, J, and H. So B, J, H. And then next, let's look at E. So E can reach G, F, and I. So let's add G, F, and I. And now let's look at F. F can reach H, I, G, and E. So let's notate that in our adjacency matrix. And then next, let's look at G. Who can G reach? G can reach A, J, and E. So we can represent that. So we just represented G, and now we can represent H. What can H reach? H can reach D, C, F, and I. So D, C, F, and I. And again, we're notating if I can reach the item from here, or we could look at it there, I notate that edge is a 1. There's a connection. If there's no connection between the pair, then it's a 0. So what we can also look at is I. I can reach E, F, and H. So let's notate that. And now for our final item, let's look at J. J can reach A, D, and G. A, D, and G. So let's notate that. Okay, so this is super sloppy, but I just want to demonstrate this is what the adjacency matrix would look like for this graph. And what we can see here is that if I want to find the adjacents of A, what I do is I look up A. Who can I reach? I loop through each one of these, And if I'm doing a breadth first search and I'm looking for the adjacents, I have to find them within the row. So the time complexity of finding the adjacents, given this representation, would be big O of V, because we're going to loop through V. There's V columns, right? So it's big O of V to find the adjacents for any given node. So, okay, big O of V, that makes sense. Now what we need to also consider are the trade-offs. So the advantage of the adjacency matrix is that we can know whether two nodes are connected in constant time. It's a simple lookup. If I want to know whether A is connected to D, I look here, A, D, it's a 0. There's no connection. If I want to see if F is connected to J, F, J, we see they are not connected. The advantage this has over we'll see adjacency lists later, you're probably familiar, is that with adjacency lists, if one node is adjacent to all the nodes, at worst, if I want to know whether A is connected to J, I might have to loop through n-1 nodes, not including myself. Unless I'm connected to myself, we would have to loop through all these nodes that are upper bounded by the size of the graph, big O of V. So the issue with the adjacency matrix is adjacency lookup is more expensive, but seeing if there's a connection is less expensive. With an adjacency list, it's easier to find the adjacents. We don't need to do any work. It's already implicit in the representation. But the issue is, if I want to find whether there's a connection between two nodes, we might spend O of V time searching for that connection. It's constant time with this. That's the advantage here. The disadvantage is advantages. The other issue with the adjacency matrix is the amount of space that it takes up. So the adjacency matrix will always take up big O of V squared space. We're always going to be representing V by V vertices. So I just made a correction. G is also connected to F in the adjacency matrix, so that's just a small tweak correction there. So going back to the issue with space is if we have very few edges, but we have many vertices and very few edges connecting them, we're going to have a ton of zeros in this graph. When a graph has near the maximum amount of edges that it can have, it's called dense because we're reaching that upper bound of edges and there's many connections between nodes. If we have very few edges connecting the nodes together, the graph is called sparse. So the issue with a sparse graph represented as an adjacency matrix is we spend a lot of space when we don't have to. So that is another disadvantage of the adjacency matrix. What an adjacency matrix does is it changes the time complexity of our breadth first and depth first search. Because the graph is represented like this, we're going to, for sure, touch V vertices, but the question is, how much work do we do at each vertice? So at each vertice, we, for sure, are going to have to find the adjacent vertices that are touching this vertex reachable. And the issue is, for V vertices, we're going to, at maximum, be looping over big O of V columns to find the adjacents. So we're going to be doing big O of V squared work if our graph is represented as an adjacency matrix and we're trying to do depth first or breadth first search. And we're going to see how adjacency lists change that. And what we're going to do next is look at adjacency lists. How would we represent this as an adjacency list? So let's see that right now. So there's many ways that we can form an adjacency list. We can use a linked list. We can use objects in memory and just have an extra field that says adjacents. There's a ton of data structures way we can represent this, but let's just imagine we have an object, it has a field called adjacents, and we're just appending on these adjacents to the node object. That's how you're often going to see it represented, and you're going to manipulate it that way. Let's create an adjacency list. We're going to represent each node over here. So let me draw those. So right here we have an adjacency list. And what we're going to do is we're going to see what it would look like. A is connected to B, J, and G. So let's write that right here. This would be stored on the object. You'd say whatever node.adjacents, and you'd get this list back. So A is connected to B, J, and G. So B is connected to A, J, and D. And then C is connected to H. And then D is connected to B, J, and H. And then E is connected to G, F, and I. I know this is tedious and it's really basic, but we really have to hammer this home and really get this down. So F is connected to G, E, I, and H. And then G is connected to J, A, F, and E. And then H is connected to D, F, and C. And then I is connected to E, F, and H. And then finally, J is connected to A, D, and G. What we have here is we can see that this is a lot thinner than the adjacency matrix. We don't have V squared representations of 0, 1 values where we say, is there an edge or not? We have a very tight list here of exactly who is adjacent here, who is adjacent here, who is adjacent here. So going back to the breadth first and depth first search example, we're going to definitely touch big O of V nodes. We're going to touch V nodes, and maybe we cut execution early. That's why I upper bound it to some multiple of V. But big O of V nodes we'll touch. And how much work do we do at each node? Well, what we're going to do is we're going to be looking at maximum this many adjacents, this many adjacents, this many adjacents, this many adjacents. But how do we represent this in an overarching sense so we understand how the work is going to look like for the whole graph? So what we need to do is we need to break it down a bit so that we understand where big O of V plus E comes from. Okay, so big O, V plus E. First of all, these vertical bars mean cardinality. Cardinality is just a fancy word for size, and it measures the size of a grouping or a collection of items, a set of items. So if I have 3 items, A, B, C, the cardinality of that set is going to be 3. So let's look at our adjacency list and try to make sense of this big O, V plus E. First of all, we can see what the V is. The V is right here. These are how many vertices we have, so we can label that. So we have the V labeled there. And now what we can do is we can look at the adjacents. What is the cardinality of all of these adjacent representations? It's 2e. So we have 15 edges from our original graph, and we have 30 representations right here. And the reason is, if A is pointing to J, since this graph is undirected, J is also going to be pointing to A. So it goes 2 ways. Every node is there's going to be redundancy to some extent between these connections, node to node and then node back to the original. And this is only because the graph is undirected. If it were directed, this would not be the case. V and then 2e. What we need to do now is we need to see what does the work look like when I do breadth first search or depth first search. In breadth first search and depth first search, fundamentally the same thing happens. We pull a node out, we do some work to that node, we find all of the adjacents. If we have not seen a node, we add it. But we're still looping over all of the adjacents. Visit A, loop over BJG. Visit B, loop over AJD. Visit C, loop over H. That's what the search is going to do, whether it's breadth first, depth first. That work is still going to happen. The only difference between breadth first and depth first is the order of the search. So how can we represent this? We can represent it like so. We can say visit vertex 1, we're going to perform V1 work, and then we're going to investigate V1 edges with the for loop. And then after that, we're going to visit vertex 2, and then we're going to visit vertex 2's edges. And we might investigate the same edges. If vertex 1 and vertex 2 have shared edges, or if they're touching the same nodes together, then we're going to touch that same edge again. And we're going to see how this plays into the time complexity. So this is what the work would look like for breadth first, depth first search. V1, investigate the edges. V2, investigate the edges plus ... And then finally, we investigate the edges of Vn, or I should say Vn as well. We investigate node Vn and then Vn edges. What we can do here to make it very clear where this comes from is we can group things appropriately. If we group things like so, where we take all of the vertices, because we're going to visit all of them. If this graph is connected, we're going to visit all V of them. The grouping would look like this. So this is to represent that we're going to visit V vertices and do V1 work, V2 work, plus ... plus Vn work. So that can be bounded by V, because that's the amount of vertices we have. And then what we can also do, we can represent the edges. Let's group the work from the for loops. And again, remember, we can traverse an edge twice because these edges run both ways. So let's add that right now. So you see, we're going to do V1 edges iterations. We're going to do V2 adjacents, ... Vn adjacents. And what you can see here is that if we have an undirected graph, they go both ways. the amount of for loop iterations that we do is going to be dependent on the edges, the total amount of edges. And the maximum retraversal we can do of an edge is 2 times. We can go from A to B, and then when we're at B, we also will do a for loop. We're gonna touch A. We will not follow it though. We've already seen A. We've added it to the hash set, but we will not follow that edge. But that is still work. That is a for loop iteration, and therefore it will be twice traversed. It'll be touched twice. And this is why we have 2e to represent the amount of nodes, how they're gonna be double crossed. And what you notice is that is what this looks like. It is 2e. This is how many for loop iterations we will do if we visit every node. Think about it. We visit A, B, C, D. Each of these represent a for loop iteration. So what we've wanted all along is right there. That 2e right there is what we can do to represent this grouping right here. So let's write that. It's going to look like this. Big O of v plus big O of some constant times e. And what that ultimately becomes is the addition of these, big O of v plus e. And so whenever you see big O of v plus e, all it's saying is my work is multilinear in time or linear in time. We represent the vertices as v, we represent the edges as e. If it's undirected, we can double touch edges, but we won't follow them. And the constant on the e will go away. And that is where big O of v plus e comes from. And so we sometimes get representations as matrices. And what we can do is we can model each cell as a node, and we can model each adjacent cell as an edge. So the edges would be this. You notice that the corners have 2 adjacents or 2 edges. The items on the border have 3 edges coming off of them. And I forgot to add edges to that middle row. So, and then the items in the middle can have 4. They can go up, to the right, down, or left. So we can have 4. So again, the reason we're interested in this is so that we can see, instead of just saying big O of v plus e, how do we represent the time complexity in terms of m by n, in terms of the actual matrix itself that we're modeling as a graph. The cardinality of v is 24. 8 times 3 is 24 cells. So we have 24 cells, so v makes sense. We have our v in terms of the matrix. It is m times n. So v equals m times n, and now we need to model e. So the reason that we saw how many edges can come off of each of these cells is because what we want to do is, why don't we model it as an adjacency list like before, and we investigate what is the upper bound on the edges and how does that connect to m times n. So let's do that right now and write that adjacency list. So instead of writing out all of the nodes, we can just represent these with dots. Do the same thing as before. We'll have v vertices. And instead of v, we're going to say m times n. And now we want to represent the edges. Okay, so we saw that the corners can have 2 edges. The top and bottom, left and right, can have 3. And the center ones can have 4 connections to their surroundings. So what can we upper bound each of these cells to in terms of edges? How many edges can come off? The maximum is 4. So let's upper bound these corners as well as the top and bottom, the left and right, with 4 edges, because the maximum is 4, and I know the corners will have 2, but we're just trying to upper bound things so we can get an asymptotic understanding. So each of these m times n cells can have at maximum 4 edges coming off of them. And so we're going to keep doing that. We're going to have m times n of these 4 column rows. So that is 4 times m times n. Okay, so what we see here is that we're going to do the v work, and we're going to do an upper bound of 4 m times n for loop iterations, because vertice loop, vertice loop, vertice loop, vertice loop. What this means is we can actually express everything in terms of m times n, because if v is m times n, remember how we split things before, m times n plus our upper bound factor for m times n, we just get 5m times n. And this is, I don't know how tight of a bounding is. We could get tighter somehow mathematically, but this is sufficient enough for us to draw an asymptotic statement. And if we have 5m times n, what happens is the 5 just disappears and we just have m times n. So the time complexity for breadth first slash depth first search is going to be big O of m times n for this matrix. And let's go back again to why that's the case. So what we did was we said we have v vertices. How can we model that? V equals m times n. Part one finished. And then we saw how many edges can we have? Well, we needed to say each vertice, how many edges can come off of you? The upper bound on that is 4 because we only can have a top, bottom, left, and right for these center guys. The outside guys will have 2 or 3. But the thing is, we want a worst case bounding just so we can find the asymptotic nature. We found that the edges would be 4 times m times n at maximum because we have m times n rows of 4 edges coming off of m times n vertices. And ultimately, those are for loop iterations plus visiting the actual vertex. And that's addition. And this is, I don't know how mathematically rigorous this is, but this is where it comes from. This is the intuitive understanding I want to give you so that you can look at other graph problems, model them, find V, find E, and perform the addition. So now you have the toolkit to analyze other graph problems. And based on whatever structure represents it, you can figure out the time complexity now. So that is all for big O of V plus E. That is all for these graph time complexities. Now I think we have the fundamental basis and understanding to actually tackle graph problems and calculate our time complexities from there.